Hello. In this video I'm going to run through the calculations for a chi-squared goodness of fit test. Please take a couple of minutes to read the information in front of you. Okay, so the purpose of the goodness of fit test is to determine whether observed experimental values from an experiment or from some data conform to a hypothesized model. Inevitably, whenever you do perform an experiment, it is highly likely that you will not get precisely the expected totals from the model. There will be some variation. The question is the variation too much? Is the departure from the model too great? Does that then suggest that at least one of the conditions of the model is incorrect? It certainly does not mean that every condition of the model is incorrect. It just means that the departure from the theoretical values doesn't conform to the model as stated. So there could be one thing or more wrong with the model. So, what is the model going to be? We have a game which consists of 4 trials. Each trial is independent, and then counting the number of successful outcomes. Sound familiar? Well, the null hypothesis, according to the questions about the claim, is that the probability of success is 0.6. The alternate hypothesis, therefore, is that the probability of success is not 0.6. If it were 0.6, then the conditions of the binomial are met. The number of successes should follow a binomial with n equal 4 trials, and the probability of success is 0.6. We know that the trials are independent, so this indeed should be the correct calculation. So the probability of 0 successes should be 4 choose 0 times by 0.6 to the 0 times by 0.4 to the 4, which is 0.0256. If we have 200 repetitions of this, then if we only get 0 successes 2.56% of the time, then we would expect there to be 5.12 occasions when players got 0 out of 4. Repeating this for the other numbers gives us the following. So, note that these expected values absolutely do not have to be integer at all. We note that all of them are greater than 5, which is one of the conditions for the chi-squared. So, are the conditions for the test well met? Well, the first condition is that the data comes from a random sample, and it was stated in the question that that was the case. For sampling without replacement, just like testing for proportions and so on, we need to make sure that sampling without replacement doesn't alter the probabilities of what's left too much, so we need the population size to be much greater than the sample size. And it says that this is a very popular game in Atlantic City, which is a very popular casino town, so absolutely we can assume that there are more than 2,000 trials of this. And as just stated, all the expected values are greater than 5, so we're good to go with the test. So how do we actually calculate the test? Okay, so we're going to assume a 5% level of significance. There were 5 cells, 0, 1, 2, 3 or 4 successes out of 4. So the number of degrees of freedom is the number of cells minus 1, which is 4. So we look across at 4 degrees of freedom to our 5% level, and we find out that the critical value is 9.49. Any total deviation from the model less than 9.49 will not be significant at the 5% level, and anything greater than that will be. So the longhand calculation of the statistic is the sum of observed minus expected squared over the expected. So in our case, that's going to be 9 minus 5.12 squared over 5.12 plus 36 minus 30.72 squared over 30.72, and so on. When we actually do work the whole thing out, we find out that the chi-squared test statistic is 9.88. The total variation from the theoretical model is 9.88, and we note that that is definitely larger than 9.49. So we conclude that there is significant evidence at the 5% level to reject H0 and conclude that the probability of success does not equal 0.6. Of course, we could have performed this calculation on the TI, and what we need to do is enter the data of the observed values into list 1, the expected values into list 2, and then ask it to perform the goodness of fit test on those two lists, and we find out, as expected, that chi-squared is 9.888, and the p-value was 0.0423. The p-value confirms what we already know, the probability of getting a variation when in fact the model was appropriate, a variation greater than we have 4% of the time, which clearly is less than the 5% significance, so we have the same result. So generally, the important parts of this test is to confirm the conditions, random, 10% rule if sampling without replacement, and large counts. Calculate the appropriate degrees of freedom, which is the number of cells minus 1, and then calculate the test statistic based on the expected values from the theoretical model. Again, remember, you always need to make your conclusion in the context of the question.